Hello, and welcome to Lab 5, Part B, Exploration of Global Ocean Temperatures. The global ocean temperature data used in this lab came from the 1990 to 1998 World Ocean Circulation Experiment. The endeavor involved over 30 countries, hundreds of research cruises, and millions of physical and chemical measurements throughout the global oceans. The primary goals were to establish the ocean's role in the global climate system and to develop a baseline of oceanographic data for future research. This data continues to provide critical information for testing hypotheses and models of oceanographic processes. Understanding the data reported in this diagram requires a basic understanding of contour lines. A contour line is a line that connects locations with equal values. One type of contour line is an isotherm. Isotherms are lines that connect locations of equal temperature. For example, an isotherm labeled 10 means that all locations along that contour equal 10 degrees Celsius. Additionally, every fifth isotherm is labeled in bold, and it represents a 5 degrees Celsius temperature difference, which means that each interval in between equals 1 degree Celsius temperature change. Let's examine the isotherms more closely within the Pacific and Atlantic Oceans. Along the equator, we see the highest recorded temperatures. However, in the Pacific, temperatures in the west are higher and decrease towards the east. Likewise, in the Atlantic, temperatures in the west are higher and decrease as we move towards the east. Now let's examine the isotherms more closely in latitude. Starting at the equator, the coldest annual surface temperatures are in the higher latitudes, from 60 to 90 degrees north and from 60 to 90 degrees south, while the warmest surface temperatures are in the lower latitudes, from 0 to 30 degrees north and 0 to 30 degrees south. Next, let's explore some of the reasons behind these global surface temperature patterns. Axial tilt and the seasons. Earth is tilted at an angle of 23.5 degrees relative to Earth's orbital plane around the sun. This is important relative to how solar radiation is distributed across Earth's surface, with more heat in areas tilted toward the sun and less heat in areas tilted away from the sun. Thus, the tilt in Earth's axis results in seasonal change. Summer in the hemisphere tilted towards the sun, winter in the hemisphere tilted away from the sun, with fall and spring being intermediate. Solar radiation. Additionally, since Earth is spherically shaped, incoming solar radiation is distributed unevenly across the surface. This results in colder average temperatures near the poles and warmer average temperatures near the equator. Thus, the amount of solar radiation, or heat, delivered to any given area is dependent on latitude. In the higher polar latitudes, sunlight strikes the Earth at lower angles. Thus, less sunlight is received per unit area, and additionally, the poles are physically farther away from the sun. In the lower equatorial latitudes, sunlight strikes the Earth at higher angles. Thus, more sunlight is concentrated per unit area, and the equatorial region is physically closer to the sun. The Coriolis effect. The Coriolis effect is the bend or deflection of currents due to the rotation of the Earth. The rotational speed is fastest near the equator and slower at the poles, or essentially zero. Thus, in the northern hemisphere, currents tend to deflect to the right. In the southern hemisphere, currents tend to deflect to the left. This bending of currents creates major wind-driven ocean gyres that circulate surface waters and surface temperature patterns. These circular patterns generally occur clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Within these circular ocean gyres, warm and cold currents flow. Warm currents that are heated near the equator flow toward the poles, while cold polar currents flow towards the equator. Notable currents include the California current, which is the cold water current portion of the North Pacific Gyre, transported from the polar regions along the eastern edge of the ocean's basin to the equator, where it heats up as it moves west along the North Equatorial Current. The Gulf Stream. The Gulf Stream is the warm current portion of the North Atlantic Gyre. It's been heated along the equatorial current. Upon reaching the western edge of the ocean basin, the water is transported to the north, where it loses its accumulated heat before returning south. Coinciding with the Coriolis effect, prevailing winds flow in similar directions as the rotating surface currents within the basins. Westerlies in subtropic regions blow west to east, pushing surface waters along this flow path, while the easterlies, or trade winds, blow east to west, pushing surface waters along the equator. It's now time to complete your lab assignment. Part B, Exploration of Global Ocean Temperatures. Then watch Video 4, Part C, Exploration of Global Ocean Temperatures. Please address your questions to your lab TA.